Let's take a look at analytics-based product engineering, a solution that combines MindSphere and Teamcenter AimSim. It helps you to solve issues faster and to tailor your products based on real load cases. In the following demo, you will hear about a typical connected product scenario for industrial machinery. The storyline is about a manufacturer of quality test machines that tests the tightness of plastic bottles. They are having a globally distributed fleet and monitor the machine variables and KPIs via MindSphere. Currently, some of the machines are facing output drops in different locations on one specific machine type. In this storyline, the customer service manager gets called up by one of his customers, telling him that the output of the machine goes down after the head was replaced a week ago. The customer service manager checks this on one of his dashboards in Visual Explorer and can confirm that not only the machine in Dallas is not performing as expected, but also the locations in Salvador and Mumbai seem to have problems. In the next step, he wants to find out what the exact problem is. In this step, the customer service manager opens up the standard application Fleet Manager. He has a look at the events that occurred over the last day. Besides some other issues, he can see that there are many issues related to overheating motors. This is not something that he can fix by himself or with his services team, but also wants to report back into the engineering department. Most of the issues are related to the overheating problem, and that's why the system engineer needs to further analyze the issue with the MindSphere tools. He sets up a special dashboard in Visual Explorer. This dashboard symbolizes the motor curve of this specific motor. It shows the torque over the rotations. The red dotted line shows the boundaries of the connected motor. By looking at the blue measured data points from the motor, he can see directly that the load is too high for the installed motor and it is operated close to its limits. He needs to make the simulation engineer aware of that problem. The simulation engineer opens up the system simulation application. The system simulation application gives her the chance to run her simulation model of the quality test machine based on the real load cases gathered from the field. She has set up already a digital twin template, which links the simulation model with the real-world asset. In this case, it is the quality test machine in Dallas. In the System Simulation application, she goes to Workbench and opens up the Studies tab. A study is one specific parameter set for certain variables in the simulation model. Later, she can perform runs with time series data on the different studies to test which model parameter set shows the best results for the real-world behavior. For the problem, she has set up already a couple of different studies. The first study is the problem verification study, where she didn't change any parameter in the simulation model to see how the temperature rises over one production cycle. To solve the overheating issue, she has to come up with two different solutions. For the short-term fix, she has two ideas. The first idea is to increase the cooler surface of the motor and add active ventilation to it to reduce the heat on the motor. The second idea is to slow down the lifting and lowering of the head in the machine. For the long-term solution, she has come up with a new motor specification which she wants to test against the real-world behavior. Now it's time for her to test the different parameter sets for a typical production cycle of the machine. After she performed the runs for the different studies, it is time for her to analyze the results. For every study, she has set a temperature threshold of 70 degrees Celsius. If a run is marked as red, it exceeded the threshold during the simulation. If a run is marked green, it stayed below the 70 degrees. First, she analyzes the problem verification run and sees that the temperature rises throughout the production cycle beyond 90 degrees Celsius. For the cooler surface adjustment, she can ignore the first configuration because it went beyond the 70 degrees. It is more interesting for her to compare the slower lifting with the cooler surface adjustment. She selects both runs and opens the comparison. There she sees that the temperature of the cooler surface adjustment comes out a little bit lower than the slower lifting. But considering the efforts to implement both solutions, she decides for the slower lifting, as this is a software fix that could be deployed immediately. The cooler surface adjustment would require a design change, several manufacturing steps, and finally a service operation to attach it to the machine. The last run also confirms that her new drive design will prevent the motor from overheating again. In case an in-depth analysis and optimization is required, the simulation engineer can also download the MindSphere time series data and run the simulation in her local Siemens AIM-Sim installation. In her last steps, she submits the new information to the system engineer so he can work with the product manager on the software fix and design changes. After the implementation of the short-term solution, and then following with a retrofit of the replacement motors, the customer service manager checks his dashboard again and can confirm that all machines are now performing as expected.